Hello, I'm Michael Ernst. It's a great pleasure to welcome Kathleen Fisher from AT&T Labs for our colloquium today. She's a distinguished researcher in programming languages, and she's done a variety of work, everything from object orientation to multiple projects that deal with large amounts of data. She's going to be talking about that today. So thank you.
Thank you. Thank you for the invitation to come and speak for you. I'm honored to have your attention. As I'm giving the talk, please feel free to interrupt and ask questions. It's more fun to be interactive than to have me talk for an hour. If it starts having too many questions, I'm capable of saying that's enough for now and I need to finish. So feel free to interrupt. Right. So start out with the observation that as I've been hearing about all day, you guys are very familiar with the fact that there's gobs and gobs and gobs and gobs of data out there, lots of it in databases and XML. And if your data happens to be in one of these two formats, there's tons of resources available to you to help make the data more manageable. Everything from schema and browsers and query languages to consultants that you can pay to do the job for you if you happen to have enough money. So if you're in that situation, things are good, but we're not always so lucky. There's tons and tons and tons of data that is in ad hoc data formats, chaotic formats, not in XML, not in relational databases. And if your data happens to be in one of these forms, you really have very few resources to help you. You end up writing your own tools in Perl or awk or C, rolling your own tools all the time. So this is to deal with various kinds of ad hoc data. So ad hoc data, what exactly is ad hoc data? Well, the best way to define what I mean by ad hoc data is by giving you a bunch of examples. It's one of those things, it's like you know it when you see it kind of thing, but it's hard to actually kind of define. So this slide is government statistics about energy usage or production and 1970, it's historic data, so this is from 1973 to 1980, this particular snippet. It has at the top a header row that tells you what each column means, and then it has the actual data. The first column is where the data comes from, the second one is the time. Notice that the time here, you may not be able to see it, is a 4-digit year, 2-digit month, but the month's actually 13, which seems a little bit odd. Turns out 13 is the summary for the entire year. There's also other records that have 12 and 11 and so on. And then the measurement, the units of the measurement, and it turns out the data can come in different orders, and this number tells you what order the data is coming in this particular instance. This is another example. This is a train station data, giving you information about commuter rail stations across the United States. It has the name of the railroad authority, the location, and then a list of counts of the number of railroad stations in the particular system. The U's are unknown. They didn't know how many railroad stations they had in the particular year. It's a little bit odd, but seems to be the case. And if you notice, like the numbers here go up, 45, 46, 46, 47, 51, unknown, 45. Did they lose 6 railroad stations? No, in fact, the data here, the first, I think 7 columns are total railroad stations, and the second 7 columns are handicap access stations. So the numbers go down because not all of the railroad stations are handicapped access. So then this one perhaps is more familiar to computer scientists. It's just the common log format. Whenever you make a request of a web server, it records in a log file summary data about your request. This next example is from the biology, from the field of genetics. It's a tree-structured data structure that records species and genetic information that talks about how far species are apart from each other. So the kind of question you'd be asking if you had data like this is, how closely related are pongos and chimpanzees? So those are all examples of ASCII ad hoc data files, but not all ad hoc files are ASCII. This is an example of a binary file that happens to be the binary representation of compiled Haskell files. But this is another data file that has information in it. It's just an example of a binary one. So those are just give you a sense. There's also COBOL ad hoc data files that AT&T sadly has many of. Right. So those are examples of what they look like. This table summarizes some of the ad hoc data files that AT&T plays with on a regular basis. The left-hand column describes kind of what the purpose of the ad hoc data file is. The middle column describes what its representation is. And the right-hand column describes kind of how big the particular data file is. So what you can take away from this is that there are lots of different kinds of representations. There's ASCII, there's binary, there's COBOL, there's fixed width, there's variable width. And then on the right-hand side, you can take away like this bottom one in particular. It's basically as large as you want. If you can process the data, someone can supply you the data that's that size or bigger. So basically, you have to be able to deal with as much data. The more data you can deal with, the better your system is. So AT&T cares a lot about this kind of data. So that's just one industry, but basically many, many industries, many scientific fields have similar kinds of problems. They have gobs of this kind of data that they have to process all the time to be able to extract useful information. So there's a lot of it. It has a lot of useful value, but why is this hard to deal with? The first is the data is, it arrives as is in many different encodings and formats. You can't say, well, I appreciate that you sent me the data, but it's not in the format I specified. Can you please send it to me in a reasonable format? That's just totally non-starter. All you can do is say, thank you very, very much for sending me the data. Now I have to figure out how to be able to use it. So you can't say no. You have to just say thank you. The second is the documentation for this kind of data is often out of date or non-existent. It's quite common to have the documentation be an email message somebody wrote 3 years ago describing what they were able to understand about the data before leaving the company. So all you have is this kind of out-of-date email information. It's really common to have what we call hijack fields, where you had some data representation and you had some column of that data or some piece of it that you thought was going to be really important. But over time, it turned out it wasn't really important. And so you stopped populating it eventually, or you keep populating it, but nobody uses it. And then you discover there's some other piece of information that's really valuable that you'd really like to keep, but there's no place for it. If you change the format, all of your tools will no longer be valid. You'll have to start all over again, and you can't afford to do that. But you notice, wait, there's this field that nobody's using. I can go and stick my data into that field, and everybody will be happy. Except the email message that was stored doesn't get updated. So nobody's documented the fact that this field now means something completely different than it did before. It's also really common to have undocumented missing values. So it's very common to have missing values. And instead of having sort of a standard representation of missing values, each person seems to invent their own representation of missing value. So we saw in the railroad station example, there was the letter U to say unknown. Other common things are to leave it blank, or to put in a dash, or to put N/A. There are many different representations, and typically those are not documented. The next challenge is that the data is usually buggy. So most of it conforms to the intended representation, but not all of it. Sometimes the data is missing because a sensor went offline or because a system went down and wasn't able to provide data. Sometimes the data is being supplied by humans, and humans are terrible at data entry. Basically, you're guaranteed to have lots of errors if a human touches the data. Sometimes they're like race conditions. A lot of ad hoc data comes from logging of systems. And logging is a low priority item for all of those systems. So they typically don't want to take the time to get a lock and potentially have to stall to get a lock. So they just write to the file without getting the lock, which causes messages to get interleaved. And so you get really random outputs. But then you have these errors that you have to deal with. And then the question is, well, how do you deal with them? What do you do with them? And here the problem is different applications, the errors have different utility to. Some of the errors, the analysts are dealing with so much data that they really don't care about the error cases. They just want to throw them out and not worry about them. They just want to deal with the clean data. But in other cases, the errors are the most interesting part of the data. If you have systems that are trying to interoperate and there's a problem like with contention, the log file getting corrupted is often a symptom of the system entering a bad state. And that bad state is exactly what you're trying to find. So the error conditions, how you respond to the errors is really application specific. Right. And then lastly, these data sources tend to be really high volume. And basically, high volume makes anything much more difficult. Right? The size of the data are such that a human can only look at a tiny fraction of the data. And it's really hard to get intuitions about what's going on when you can only look at a tiny piece at a time. So that's why it's hard. What do people typically do? Well, being a computer scientist, people say, oh, ad hoc data, that's a parsing problem. We know how to solve parsing problems. We use Lex and Yak. Well, not really. None of the people that I've ever interacted with who deal with ad hoc data files use Lex and Yak. I think part of the problem is it's sort of overkill. You end up having to write a lexer and a parser in two separate files, and so you end up having a specification that's split over two different places. And also, it's a sort of overkill. It's making you work too hard for the parser you get, but it's also not giving you enough in exchange for the time that you put writing the parser. And we'll see a little bit more about that later. So what people really do is write Perl and C code. And this is really not a good solution. It tends to be really brittle with respect to changes in the format. Right? Perl is often described as a write once, read never kind of language. So if your data format changes and you have to go back and understand your Perl code, you're left trying to read Perl code, which is not typically very successful. often you're tasked with, given this data format, answer these kinds of questions as fast as possible. Like you have the minimum amount of time to answer those questions. So you write the parser as fast as you can, which means your analysis code often ends up embedded with the parsing code, which means that that parsing code is really hard to be reused for other kinds of applications. And then there's the problem of the error detection. So here you're kind of damned if you do and damned if you don't. Remember we said that the data files typically have errors. If you write all the error detection code to catch those cases, your code ends up dominated by error checking code. And then it's really hard to use the parser as documentation for the data because all you can see is all the error cases. It also means that it takes way longer for you to write all that error detecting code. So the flip side is you don't put the error code in, and some error slips through, and if it's going into some long-term data storage system, that data could be extremely valuable, and you've now corrupted it by not checking. So there's basically no good way to deal with errors in this case. And everything has to be done by hand, so it's a very labor-intensive process. Okay, so types to the rescue. So we talked about, I claimed that relational data and XML was much easier to deal with. And one of the reasons why these data formats are easier to deal with is they have a notion of a schema that has the computer be able to help manage the data. So relational data has relational schema, XML have XML schema or DTDs. Is there a corresponding notion that we might be able to use for ad hoc data? And the answer, this is what I'm going to talk about today, is yes. You can have a notion of what I call physical types. And the thesis is that basically physical types can facilitate dealing with ad hoc data in the same way that DTDs, XML schema, or relational schema facilitate dealing with data in XML or relational form. And furthermore, that the types that we know and love from programming language theory are perfectly suited to this task. Okay, so how is this going to work? So we have our sample ad hoc data format up here. This is just the energy one that I talked about at the beginning. And we're going to describe that by a physical type. The physical type is going to correspond to a standard type, that this is a type that you would use in your programming language, and that there's an easy way, an erasure, that will go from the physical type to produce the standard type. So this will describe this data format in detail, and this will be the corresponding data structure, and we can map a value of the physical type into the standard type using a parser, and we can go back using a pretty printer. And I'll explain all those pieces in more detail in the next bunch of slides. So at this point, I've sort of set up the stage of what I'm going to be talking about. And this slide gives a roadmap of what I'm going to be talking about for the rest of the talk. The next section, I'm going to be talking about how physical types allow us to describe the kinds of data formats that I've been showing you. Then I'm going to talk a little bit about how physical types differ from standard types. And talk about other connections between programming language ideas and the problem of ad hoc data description. Talk about physical type inference, and then conclude. Okay, so this section I'm talking about how the physical types allow you to describe ad hoc data. So the first notion is when we look at this kind of data format, we can see things that we intuitively have a notion of what the type of it is. Like this is a string, and this is an integer, and this is a float. So we can have types, base types, that convey exactly that information. We have strings, we have integers, and we have floats that describe the physical representation of those things. But of course, that's not enough. It's not just that the file has string and float and int. We have to specify what the order is. Well, tuples are a construct from type theory that allow us to specify order. So here we have a tuple type that says, well, it's not just string, int, and float. It's a string followed by an integer, followed by a float, followed by a string, followed by an integer. So that conveys kind of the semantic content of the file. That's not enough, though, because there are those extra punctuation characters in the ad hoc data file that are really common to ad hoc data files. So we have like this quotation character and this quotation character and that comma and that comma and that, right, commas and so on. And so here what we do is we add this kind of thing, which is called actually a singleton type. So a singleton type is a concept from type theory. It's a type that has a single value. So the singleton type of comma is the type of the comma character. That's it. So this is the type of the quotation character. So this type now says that a record of this format is a quotation character followed by a string, followed by quotation, followed by comma, followed by int, followed by comma, followed by float, followed by comma, and so on. There's still one more problem before we have something that we can actually use to describe this data, though, and that's this notion of string. Right? What constitutes a string is sort of in the eye of the beholder. In theory, generally, you could say string is the whole of the data file. So you have to have some way of specifying when the string is over. And so we have a notion of a simple dependent type. So a dependent type is another notion from programming language theory. It's a type that depends upon a value. So here we have, this is a dependent type here, string, that depends upon a value. And what this means is this is the type of all values up to but not including a quotation character. So here, this quotation will match this first quotation. This type will match everything up to but not including this quotation. So that's TJ bus. And so on. So now this description is the first one that I've shown you that actually is a valid PADS description, that from this code you could actually generate a parser that would parse that particular data. But of course, it's still not completely satisfying, right? Tuples are good for ordering, but they're not very descriptive, right? You don't know what these strings, floats, et cetera are. But of course, there's the notion of record from programming language concepts that allows us to introduce names for these components. So now we can say that it's not just a string, but it's the source of the data. It's not just an integer, it's actually a date, and so on. So we can introduce useful names for these components. And again, this description will parse the data. It's a perfectly valid data description. Now we need to switch data formats to get the next example. We talked about the railroad data that had the U character to represent missing data. So here we have a piece of data that's either an integer representing the number of stations, or it's the letter U representing you don't have the information. So we can express that as an anonymous union, saying, well, either it's the singleton type of the letter U, or it's an integer. And that would describe, say, the numbers in this column. But it's useful to be able to give, again, descriptive names. So we can introduce a named option type, opt-int, to be either it's unavailable of the singleton character U, or it's available of int. So these tags will tell you which branch you're in. So that characterizes that, options, choices in the data. But we also have repetition. So here we had the list of all of the stations. So we'd like to be able to express some kind of list or iteration construct. So here we have an array construct that says we can define a type counts that is equal to 14 optional integers. So opt-int is this type that we've just defined, and 14 is a length. It says that's how long the sequence is. Of course, that's a little bit brittle, right? It may be this year the length is 14, but next year it might be 16 as we add, hopefully, 2 more data points on how many stations we have. It's not just a list of optional integers, right? There are these comma characters. So in the array, we have to also add this piece separator that specifies what kind of thing is between all of the elements of the array. So here, this is a modifier to the array that takes as an argument a type that specifies what kind of thing appears between all of the elements. And then, as I said, it's kind of brittle to say 14, so we have an option of a form of the array that allows us to specify different kind of termination condition. So here, this is another modifier to the array that specifies it should stop as soon as it sees the singleton type of end of record. So what this means now is that we will have an array of optional integers separated by comma and terminated by the end of the record. So now it will go continuing to consume integer, comma, integer, comma, integer, comma, and so on until it gets to the end of the record. Questions? Yeah?
Why is there no comma at the end of the record on your example?
Why is it no? So the separator is intended as a separator, so it's between the elements of the array. It's not after every single element of the array. If you had something that was in every single element at the end, that would just be part of the array element description.
I don't understand. For example, in the last row, you have a bunch of U's followed by the 18 right there where your marker was.
Right, so here there's an 8, but there's no comma here.
Yes, that's my question.
Right. So
wouldn't that be in the record after the 18?
So there's the data format itself has no comma there, so we have to be able to cope with a situation where it has no comma. The semantics of separator is it's the thing that's between the elements. So between does not mean after. It's just so there isn't. This description says there's no comma afterwards. If you wanted to have it, if it was there, you'd have to do something different to describe the fact that it was there. You could put it inside the element type, or you could say it's an array terminated, that terminates under different conditions. Another question?
Recursive types?
We do have recursive types, yes.
So then hypothesis, any regular expression could be translated into this language,
Yes.
but not vice versa?
Yes. Yes, PADS is a superset of regular languages. It's a little bit incomparable with context-free languages because of of dependency and context-free. So we can easily recognize A to the n, B to the n, C to the n, for example, which is not a context-free language. Right. So dependency is what I want to talk about next. So this is a fragment of common log format. It's the web server log. When the server gives a request, it writes data to a log file. And the piece I want to describe is the second to last column, which is the integer response code. So it's an integer, But we know more than that. It's actually an integer that has to be between 99 and 600. So we can include that documentation in the pad's description by defining a type response code that is equal to the set of all integers such that that integer is between 99 and 600. So this is a way of, the idea is that the pad's description should include all of the information that you know about the data file. It will be the source of information about the data file. We posted on a library. If there's a website that was the repository for all information about this data source, that would be the pad's description, that anybody who wanted to go use the data source could go look at the pad's description and use it to generate the tools for manipulating the data. So everything we know should be in that description. And this gives us a way of including things like range information. Yes?
On the previous one, with the end of record, why didn't you use a dependent type there to mark the end of the array, and sort of as you did with the quotation end of string?
Well, you need to specify, well, there are different kinds of termination conditions, but the most general one is this, where you give basically in general case, it's a type that specifies what comes next. So dependent type is just one instance of what could be here. This just happens to be, end of record is a value, so and making it a dependent type is just another instance of everything else that you're doing. In the theory, you can have it be any other type. It doesn't matter. There was another question? Yeah?
I had a question, but wouldn't it, on the next page, in this case be more sensible to define the values that can have, for example, 201, because 250 is not possible in this case.
So you could do that as well. You could refine, and this is just a short example for expository purposes, but you can write arbitrary code, and that just has to be a predicate that takes a value of this type and returns true or false. So you're allowed to do whatever you want in that context. Okay. So in fact, this slide shows a little bit of that example. So now this is describing the get request part of the web server log. So a get request is the method that you want to use. So either it's get or post or link or unlink. This is an example of an enumeration is another type that you can use. And now you have the URL that you're asking for and what mode of HTTP you're using. And then there's a constraint that says certain methods are obsolete after 1.1. And so you want to be able to check that if you're using a link or unlink, then it must be version 1.0, I guess, or earlier. And that is encoded in this predicate. So here, after you parse a particular record, you run this predicate to return true or false, whether that was a valid instance. And here, again, this is arbitrary code. You can write whatever you want, and it has in scope all of the values that it's parsed previously in the record. So this is a more general use of dependent types.
And what if it fails?
Right. I will get to what happens if it fails in a few slides. Right. So at this point, I've sort of given you a high-level overview of a bunch of the features of pads like data description languages. They're base types that describe atomic pieces of data. They're tuples that allow you to do sequences. They're singleton types that allow you to capture the case where you have a single value that is allowed in a particular context. This is really useful for describing kind of the punctuation in the file, commas and white space. Records allow you to give names to those pieces. Unions describe alternation, lists, or sequences. Dependent types allow you to express extra kinds of properties. I haven't shown you, but there are perfectly good reasons why you would have value abstraction and type abstraction and recursive types and pointers. All except the pointers are actually implemented and available in the system. And I can show you that afterwards if you're interested. Okay, so that's sort of you can see the very close correspondence between all of these kinds of types that have been developed and played with in programming languages and programming language theory for a long time. There are, however, pretty significant differences as well. So in a programming language, when you're designing the type system, you, the person designing the type system, have total control over the data, the format of the data that has that type. That's one of the things you get to play with as a language implementer. That's totally not the case here. Here, the data format is determined by somebody outside in the world, and you have to describe it. And that leads to the fact that types have extra information associated with them, like the separator and the terminator in the array case, to cope with this extra kind of punctuation. It also means that many different physical types will end up mapping to the same internal type. So for example, there are many different encodings of 32-bit integers. There's binary encoding, there's unsigned, binary. There's COBOL encoding, there's sign bit high, big endian, low endian, all those kinds of things. We have base types for describing all of those different kinds of things, but they all map to the same internal representation. Similarly, dependent types are not particularly important, at least historically, in terms of programming languages, but they're really important in data description to be able to capture things like constants in the data stream, predicates over the value space. And also, I didn't talk about, but with unions, it's really common that you have some header part that tells you what kind of union is coming. So a format that's very common is you have a header that tells you what kind of thing the payload is, and then the type of the payload depends on that header. So in this kind of language, you can basically, you parse the header, and then you have a dependent type that says, well, if the header was form 1, it's this form. If the header was form 2, it's that other form. Similarly with arrays, it's really common to have some integer that tells you how long the array is going to be, and then the actual array. So in that case, you would use the length of the array, but you'd have a dependent type that tells you how long that array is going to be. So dependent types are much more important in the physical data space. And then the final piece is, in programming languages, you're guaranteed that if you have a value with a particular type, the value has the representation that you expected. And that's not true in this case either, right? We have to deal with the fact that data has errors all the time. So we have to cope with the fact that the data that we end up using a particular description to parse may not match the description at all. So how do we cope with that? The technique is to use metadata. So here, when I talked about how the physical type, there was a standard type, we generate not just the standard type, but also metadata. And we generate this when we process the physical type, then the parser returns not just an element of the standard type, but also metadata that describes whether or not any errors happened during the parse. So in the case where you asked about what happened if the predicate didn't hold, it would still set the in-memory representation to be the integer that it actually found in that case, if it was, like, say, 1,000, too big for the range. But it would set the bit in the metadata to say that there was an error in the data. And the error data is structurally isomorphic to the real data, but also sort of accumulates up the tree. So at the top level, it tells you how many errors there were. And if it's 0, you're guaranteed that there were no errors anywhere in the file. If it was more than 0, though, you can walk down the structure of the metadata to find if there were errors in the part of the data that you cared about. So you can isolate exactly where the error happened if you're interested. So it's really common that analysts will have a data source where they don't care about errors in part of the data. They only care about the errors in the part of the data that they're going to be using. So this metadata structure allows them to check really quickly if there were any errors, and if there were none, continue processing. But if there were, they can then walk over to see, well, were the errors where I cared about? If they weren't, then I can continue processing. Otherwise, do some more expensive analysis of the error. Questions about that? Okay. Right, so I've been talking about pads. There are actually two examples of pads. There's pads C and pads ML. So C, so there are all these expressions where the type depended on some host language. And I've been explaining that in terms of pads ML syntax. There's also pads C where the host language is C. A lot of the AT&T developers used C as their language, so it was a sensible choice to target what they were most familiar with. Once you have it in memory, it's really useful to do data transformations on, and then ML and pattern matching and higher order functions make ML a really nice language to play around with, which is why we've built a version for ML. There are other work by other people. Packet types and DataScript are examples of domain-specific languages for describing binary data that have similar characteristics to pads. They have less robust handling of error kinds of conditions, and they're specific to binary. Erlang has a similar thing for dealing with bit types, and Daffodil is a standard that's been developed at IBM sort of after this work for using an XML syntax for describing data formats. So there's a question, of course, when you have all these different languages that share kind of goals and general outline, well, how are they actually related? So we developed a core data description calculus that sort of designed to capture the essence of a data description language called the DDC that's based on dependent type theory that has sort of simple orthogonal and compositional types that allow us to build up sort of these data descriptions from these simple pieces. And the semantics of these types, that they transduce the on-disk representation into a corresponding in-memory representation. And we proved that the sort of semantics guarantees that the data, once you parse it, the in-memory representation conforms to the type that you specified as long as the parse descriptor says that there were no errors generated. And then we use this formal system to show, basically, to define the semantics of these three languages, R systems, but also DataScript and packet types, to show how it basically allowed you to compare their features on an equal footing in the role of this calculus. So then once you have this data description, you have a huge win, right? Because the data description basically tells the computer what the data means. And once the computer knows what the data means, it can do a ton of stuff for you. So what we've done is you take the PADS description, you pass it to the compiler, and you get out a parser and a printer, but you also get out something that does statistical analysis to give you a bird's eye view of what the distribution of the data is. We give out query support that allows it to connect into the Galax implementation of XQuery, so you can use XML query language to query your ad hoc data without actually having it be translated from its native form into XML. Or you can decide, I actually just want this data in XML, so I can use all of the XML tools that are available to process the data. So we can generate that XML for you and a schema that describes the data that we will have generated. And connections into tools to do visualization as well. So all of this is possible because of type-directed programming, which is a branch of research in the programming language community that lets you operate over the type structure to generate code specific to that kind of type. And means that all of these kinds of things can be implemented by walking over the type structure that we've generated. So in PADS-ML, a third-party library writer can implement these things given, that will work for any description. So basically, if you want to write a new kind of tool, say a different kind of statistical analysis, you can write that analysis in a way that it will work for any possible PADS description generated in the future. So it will be a generic tool for any PADS description. Question?
I want to clarify, your definition of type seems to be different than the definition I grew up with. Could you clarify your meaning of type? To me, it means integers, strings.
So integers and strings are base types. They're atomic pieces of types. We also have things like type constructors that allow us to build more complicated types out of simple types. So a tuple type would be a sequence of types. How the compiler chooses to represent that is up to the individual compiler. It could just concatenate the things together, or it could give pointers to the atomic pieces of data. The terminology I'm using is standard in the programming language community at this point. Or I'm intending to use it that way. I might have said something.
Sometimes I look behind them.
No worries. Is that?
No. That explains it. That helps. Yes.
Okay. Right. So the import of this is that you can write new tools that will work for any PADS description using type-directed programming. So there's a huge lever to be able to throw at this problem. So an example of that is the statistical analysis. So here, it's an accumulator that basically, given a PADS description and a bunch of data, will run over the data and put each record in turn in the accumulator and count up sort of what it saw in each of the leaves of the description. So this is an example of the accumulator report of the length field of the web server log example. So it's going to go over all of the records in your web server log example and characterize what were the integers that it saw. So it's going to report how many good integers it saw, how many bad ones it saw, what the minimum value was, what the maximum value, what the average, and then sort of what the top 10 values were. So this allows you to get a bird's eye view of, say, in this case, the length field of the web server log example sort of for free. Once you've written the description, you can get this report out just by pushing a button. And so one of the things that you can see here that may be surprising is that some of the length fields were bad. And if you go back and look at it, it turns out that the server doesn't have to report a length field. It can instead print a dash saying it didn't actually calculate this information. And so this is a sort of automatically generated tool that will show you that information for free without you having to do any additional work. So this is an example of one of the kinds of tools that you can write using the type-directed programming from a PADS description. Right. So then other ideas that are relevant from the programming language community. So one would be, is a particular PADS description well-formed? So for a union, for example, you might have two branches that overlap. So a second branch may never occur, which you would think of as perhaps a bug in the description. So you could write an analysis that would be able to figure out this answer. Or when do printing and parsing compose? Are you guaranteed that if you print something and then parse it again, I guess if you parse it and then print it and parse it, does that match what you originally got as parsing? And these are all kinds of questions that you would ask, that you could ask using techniques from the programming language community. The one that I'm going to talk about in detail, though, is the type inference question. So basically, type inference is you're given a program, can you automatically infer the type of that program? And in this ad hoc data setting, the analogous problem is, given a bunch of data, can you automatically infer what the PADS description for that data is? So this is the description. So the answer is yes, actually, perhaps surprisingly. You can often infer things that are useful. You can't do a perfect job, but you can do way better than nothing. So this is an architectural schema of how our format inferencer works for the PAD system. We start out with the raw data, and then we chunk it into units of repetition. So the whole thing works on the premise that you get multiple positive instances of the thing you're trying to learn. So each chunk corresponds to one positive instance. So a common chunker is new lines. You just divide the input file on new line boundaries. Another chunker is a file boundary. You have a whole bunch of files. Each one is an instance of the type you're trying to learn, and the chunker is just the thing that gives you all those files. It's also possible to define your own notion of kind of paragraph, which might be 2 lines starting with a pound sign, or various ad hoc formats have different kinds of notion of what a paragraph would be. But you could write a predicate that would divide that up to be a chunker specific to a different kind of data. Then at this point, we have the input data is now a sequence of chunks. We then tokenize that, convert each chunk into a sequence of tokens using regular expressions to specify what our tokens are. We then do a structure discovery algorithm, which comes up with an initial rough approximation of what the structure of the data is, and I'm going to describe that piece in a lot more detail. Then we have an information theoretic scoring function that tells us kind of how good the description is at describing the data. And then we have a bunch of rewriting rules that we iteratively apply until the scoring function tells us we're no longer able to improve the description. At that point, we can print it out into a PADS description and pass it into the PADS compiler. So when this whole process works, we can go from raw data to PADS description, pass it to the PADS compiler, and get out, say, the tool that converts it into XML. So we can go from raw data to an XML representation by just pushing the button without having to have human intervention at all. Question?
Yes. Does this work well in cases where rather than having variable length formats that have tokens that indicate different fields, where you have fixed length formats?
Right, so this is definitely targeted at sort of ASCII-based representations that are intuitively ASCII-based representations that have redundant syntax that tells you sort of the structure of the field. So data that has positional information would require a different technique that I haven't done yet. I think that it's I think you probably can do something, but I think you need to use pretty different techniques to come up with the initial description. But that's something that I'm very interested in doing. I think the same question or the same techniques would then apply to binary data. And I think the fact that compression works for binary data suggests that you should at least be able to do something in terms of format info for binary data, because both are taking advantage of sort of patterns in the data. So the fact that you can compress the data suggests that you would be able to do something. But I haven't done that. That's totally future work.
You just said we could go from raw data all the way to the data description and the tools completely automatically by pressing a button. It seems that wasn't the same as what you just described, because we have to decide what the chunks are, we have to decide what the tokens are. Okay, so it's not zero human interaction.
Right. This is true. There are default values for the chunker and the tokenizer. So if your records are new line terminated or file terminated, it will automatically figure that out for you. And we have a set of tokens that we use sort of all the time. Or there are sort of domains where you have this set of tokens is valuable for this domain, so then you can reuse those. So if your unit of repetition is standard, and if your token set is one that's already defined for, then you don't have to do those things at all. You can just go from the data to the tool. But if you do have an unusual token set, or you have an unusual notion of paragraph, of chunk, then you have to write those pieces.
In the scoring function, is there some kind of threshold or something like, if, I don't know, maybe there's some kind of, you're using some kind of probability to say, okay, if the discovery is past maybe 50% probability or 60% probability, then,
So we use a standard notion from the information theory community called minimum description length as a way of, it's basically has two terms in it. One measures the complexity of the type itself, and the other measures the complexity of the data given the type. So one is sort of how complicated a type is it, and the other is how good a job does it do describing the data. So if it does a really good job describing the data, it may be worth having a more complicated type. If it does a poor job, then it's better to have a simple type. And those two terms kind of weigh against those things. It's really just serving as a proxy for, and the goal is to have a human look at it and say, yes, that's better than that one. And MDL is just a standard proxy for that sometimes does a great job and sometimes does a less good job.
So at the end of the day, a human has to look at the data.
No, a human doesn't. This is completely automatic. It will definitely produce a description that minimizes the MDL. Whether that was the description you wanted or not is something that you have to infer. You have to decide for yourself when you get the description out. But it will do it automatically. Okay, one more question and then I need to go on.
So do you think there's some way you could use like examples of descriptions and data to like sort of learn these heuristics and like which tokens are more likely to be field separators and that kind of thing?
Yes, so I think that the answer to that is yes, and we've done a little bit of work with that, but not a lot yet. So file paths are an interesting example because you can precisely characterize what a legal file path is in a regular expression. But it turns out almost everything is a file path. And so having a token in the file that is almost, is file path that covers everything is really not useful. It means the whole thing turns into a file path. And you're like, well, okay, that may be true, but I mean, it may be technically true, but it's really unlikely that that's a file path. So having a different, more probabilistic kind of characterization would be useful. And we've done some preliminary work on that has been, it does a better job, but it's also much more resource intensive. So it's not really clear if it's a win or not at this point. So we have this is the input. It's been chunked for us. So now each one of these boxes corresponds to one chunk of the data. And the tokenizer just converts this representation into this representation, where basically each, we convert it into tokens, right? So now we have the first record starts with a quote token, and then an int token, and then a comma token, and so on. And we specify what these tokens are using regular expressions. We have a default set of regular expressions that we use most of the time. We do have the user can specify a different set of regular expressions if they're working in a different domain that has different kinds of base types. So it's a command line option to specify your own regular expression file. Right. Then the next stage is to compute a histogram that for each token counts the frequency with which that token appears in the records. So the best way to explain it is by example. So here we have the quotation character. It appears twice in 100% of the records, because every single one of these records, it appears exactly twice. In contrast, the int token appears once in 60% of the records and twice in 40% of the records. Comma and white both appear 100% once, and string appears once 60% of the time. So basically, the idea is to look for things that are stable. Things that appear the same way in every single record are there to be punctuation and are representative of the structure of the file. Well, not necessarily be there for punctuation, but they are indicative of the structure of the file, and we can leverage that information to infer a good description. So the next stage after we've computed these histograms is to cluster them, to put together tokens that have similar distributions. So we sort clusters by a metric that puts them together if they have the same shape within some error tolerance, where the columns are sorted by height. So here we end up with white, comma, and quote all being in the same cluster because they all appear 100% of the time. So their histograms have the same shape. In contrast, integer and string appear in separate clusters because their histograms have a very different shape. We then we then score the clusters on a metric that rewards high coverage, which means that they're stable, like the histogram applies all the time, and also have a narrowness, so they are always appearing the same way in every single record. So here we favor that metric rewards this cluster because it appears 100% of the time, and each of histograms has a single column. In contrast, the integer one, it has 100% coverage, but it appears in two different ways, so it's less useful as a signal as to the structure of the file. And the string one doesn't have 100% coverage, even though it appears the same way in all the records that it does appear in. So we pick the cluster with white space and quotation and comma. Now we know what the tokens are, but we actually don't know what the order of the tokens are. All we've done is count how many times they appear, not the order in which they appear. So we know that these particular tokens appear in all of the records, but not the order that they appear in. So then we go through the records one at a time, and we put the records into buckets based on record order. So for every different order we'll see, we'll have a bucket populated with the records with that particular bucket. And also we have some kind of error tolerance. So there's a possibility that some of our records won't actually have all of these tokens in it. In this particular case, the coverage was 100%, so the other chunk bucket will be empty. Also, they actually all appeared in the same order, so all of these but one will be degenerate, so we don't actually need to introduce the union in this particular case. Now we've picked an order and we've picked a token set. Now we can go back to the data and define, partition it, basically. So we go and we say, okay, we have quote, comma, white, and quote are our tokens and the order. So now we just have to definify, we have this context here that's between the quote and comma that we don't know what to do with. And we have this context over here between the white space and the final quote that we don't know what to do with. So we end up with, at this stage, we have a partial structure that says, well, we definitely start with a quote, and then we have some context that we still have to figure out the type for. Then we have a comma, we have white space, and then we have another context that we have to figure out the type for, and we have finally a quote. And now we have to recurse to figure out what the types of these two things are. We have exactly the same situation that we started with in the beginning. So we can apply exactly the same technique to infer the type of this cluster and infer the type of that cluster. So if we do that, we infer that the type of this cluster is just integer, and the type of this cluster is string or int, using the union process that was degenerate in the first case is not degenerate in this case. So that means that the inferred type for this data structure comes out to be this type, quote, followed by int, followed by comma, followed by white, followed by either string or int, followed by quote. Right, are there brief questions? Okay, so then the next piece is I just wanted to show you a demo of how this works. So this is the PADS website. So this is running on my laptop, but this is also available on the actual web. So you can go to the PADS website and play with this on your own. So this is a list of the different data files that you can run. The bottom one is roll your own, so you can enter data and have it run the structure discovery on your data. So this is just one particular data file, yum.txt. So if you push submit, it then ran that algorithm that I just told you over the data file. It presents this top box is the data format of the data that it ran over. And the bottom box is the data that it inferred, the data description that it inferred. So sorry that this screen is the type is small on the screen. But you can see here that it infers basically that the data file in its entirety, the source label indicates that this is a description of the entire data source, is an array where every element of the array is a struct 418. And a struct 418 is a date, so that corresponds to the December 10th piece, followed by space, followed by a time, which is this part. And then there's an enumeration 409, which is there, which says that either it's the string installed or the string updated or the string erased. And then there's a switch, which is one of these examples of a tagged union where some part of the data tells you what the format is that comes later. So the format of the rest of the data depends upon the format of this enumeration. And then here is describing what the format is in those particular cases. And then if you push the accumulator button, it will run that statistical analyzer over the data and give you a report. So here we can see that this particular data file had 328 records, and all of them were good. And then it gives you information about, so 119 of the records were on May 2nd, and it gives you a bird's eye view. All of that completely, right, I just ran it for you, right? From the description, it produced that tool automatically. Or similarly, the XML tool will convert the data into an XML representation, and further down is the schema that it generated corresponding to that data. Then you get a place where you can enter your own data, and then hit submit. And it will infer the data for that description. I'm sorry?
Can you upload a file?
You can't upload a file. You can copy your data into that file. There is a size limitation that the web server people made me put on so that there wouldn't be a denial of service attack against AT&T's web server. Yeah, it was a good, I can't actually have a demo of PADS on the website because if you uploaded a PADS file, you'd be uploading arbitrary C or ML code that could then run, and that would be a security hole. But since we're generating the PADS description, we figured that the security risk behind somebody uploading bad data that would then cause a description to be generated that would then cause a security hole. And basically, if anybody can figure out how to do that, they deserve to break into the system. They should just be allowed to do so. So these slides are just the demo that I showed you. So there's tons of work that we've drawn on to be able to do this work. There's lots of work on grammar induction. The work by Hector Garcia Molina and Arasu at Stanford was particularly beneficial. They were looking at the case of XML data generated from like Amazon that had a very regular structure, and they were trying to find the pieces that varied to be able to find kind of the payload part of the Amazon pages. And the techniques that they developed were our starting point for developing the structure inference. The second paper, the language identification, the limit paper, that's a classic 1968 paper that shows you can't actually do perfect grammar induction if you only have positive examples. If you have a language that has any infinite instance and finite instances, then you can't do perfect grammar induction. We use the functional dependency work from the database community to do the things like that tagged union, where you had a tag in the data that tells you which branch of the union to take. Also, we can infer if you have a length that determines an integer that determines the length of the array. We use that dependency analysis to put that correlation into the description. Right. There's tons of related work on grammar induction. Most of it is in the natural language case. So the problem that they're trying to solve is inferring grammars of natural languages, which is a way harder problem. There's work that Bex did in 2006 on finding precise methods for non-superfinite languages. And the problem is that PADS isn't, it's not a non-superfinite language. So these techniques don't really apply to PADS kinds of descriptions. There's a lot of work on information extraction, some of which has been done here. That's very nice work that requires people to label some of the data. I mean, the model there is you have like web pages that have mostly junk information on them, but then they have some key nuggets of information, like how many 3-bedroom apartments are available for rent. And you have people label examples, and then it goes and finds other examples just like that. So they're solving basically a really different problem than we're trying to solve. And then there's work on inferring X schema from XML data. And again, that's a pretty different problem because they don't have the problem of how you tokenize the data, because XML comes with its own tokenization scheme built in. And also the tree structure of XML gives you a big leg up on figuring out what the structure of the data is. It's still not an easy problem, and this is really good work, but it's quite a different problem from the one we're trying to solve. Okay, so I just wanted to conclude by saying that, summarize what I talked about. So ad hoc data is pervasive and really difficult to deal with. Data description languages can make it really much easier to deal with. Programming language ideas can make it are a good source of inspiration for how to deal with ad hoc data. Types we can use to describe the physical layout. Type-directed programming allows us to generate tools that will work over any instance of data that has one of these descriptions. So it allows us to write really useful sort of mega tools that will generate tools for each particular instance of the data. Right, and then we can use type inference to generate descriptions automatically that we can then manipulate by hand. Right, thank you. And this is joint work with tons of other people. Some of them are on this slide. There's a complete list on the website. More questions? Yes?
So of all the different kinds of ad hoc data you can get, what's the worst kind for you?
For the learning piece?
Yeah.
ASCII data that's masquerading as binary, or binary data that's masquerading as ASCII data. So if the redundancy, if the information in the file is positional rather than punctuational or syntactic, then we can't really figure, these techniques won't work for that kind of thing. You have to use some other, the techniques you'd have to use for that are the same kinds of techniques you'd have to use for binary data, entropy-based methods. I think that you probably could do something, but we haven't done that. So if you pass it data that's of that characteristic, that like column 13 means this, column 14 means that, completely independently of the text around it, it will produce a huge, not very useful description. Completely useless description, I would say. You can use PADS to describe that, no problem. Right? PADS is perfectly good at describing that kind of thing. PADS is perfectly good at describing binary data. It's just the inferencing system is not at all targeted at that application area, or that kind of data. It's not been the most important part for our users at AT&T. Question?
Just talking about the PADS description language, do you think that would work for multimedia data?
Yeah, I mean,
deal with compression.
So the issue would be you'd have to be able to decompress the data and then describe the decompressed data?
I suppose, yeah, you'd have to say there's basically a block here that's compressed like this, decompressed, and
right, so you could have a sort of staged notion of, so we don't currently do that. Right now you would be able to specify the PADS representation of the uncompressed data or the PADS representation of the compressed data, but there's nothing that would connect those two together. Right, you could think about having, being able to type some kind of function space that would say, you know, the uncompressor takes something of this PADS description and produces something of that PADS description type. So you could definitely describe it in that way, but that's not something that we've done. In terms of describing sort of the uncompressed format, PADS should be able to do that, no problem. We've defined little pieces of various multimedia formats. Sometimes it's a bit hard to find the documentation that allows you to do that, but yeah, PADS describes the binary data, no problem. Question?
So it seems like PADS helps you describe ad hoc data, but from my understanding, it's not like it helps you like find patterns or.
Right. So PADS. I mean, there's there's a huge pipeline of going from raw data to useful information, right? And PADS is at the sort of one extreme end of that point. It's just past the data collection, but it's the thing that lets you sort of take the raw data and then put it into a form that you can then start running pattern recognition and other kinds of more complicated analyses on. Because if you want to run those kind of complicated analyses, you have to get the data into some form where you can do that. And that's what PADS is designed to do. In the back?
It's kind of related to that answer. Way back on the first slide, you said that some data had a column that was month and 13 would be
right.
a summary of the year. Can PADS capture that information, that 13 is a summary? Can you document that in your description?
What you could do is, right, you could define an enumeration for month of the year that was, April, January, February, March, so on, up through, and then you could have, instead of ending at December, you could say comma summary, and you could bind those meanings to January is 1 and February is 2 and summary is 13, and then you could, in the type, you could describe that as that type that you just introduced. So you can document it to that extent, which is pretty accurate. The notion that it's a summary is, so you could write that potentially as a predicate if you were guaranteed to have all of the information. You could sort of write something that summed up all of the values previously and that was supposed to equal the summary piece. I doubt people would do that, but you could, in theory, do that. Question?
Do you think there are any benefits from putting a human in the loop when you're trying to learn the...
Oh, absolutely, yes. So for example, the inferred descriptions have no way of knowing that this particular IP address is a source and that one is a destination, for example. It's just going to say, it's going to introduce a label IP1 or IP2. So introducing sensible labels. Also, the way that a human would decompose something might differ than the way that the computer thinks is the best. Like the computer can sometimes find ways that will, basically the MDL is generating how well you can compress the data with the description. And sometimes you can compress it more than the human would actually think is a good idea. So in fact, we've been working on making this iterative. So the description that the system I've described for you takes raw data and produces a description. The new system takes data and potentially an initial description and will revise that description so that it covers everything it did before plus all of the new data. And this allows us both to scale to much larger data sets and also to allow the human to go in the loop. You can start by writing an initial description that covers part of the data and then have the system automatically refine it, or you can have the system produce a candidate description that you go and then refine, and then as the data evolves over time, you may need to update the description. You could update it by hand or you could pass it to the inferencing system. So we have a prototype that does that at this point. We're still tweaking some of the details, but definitely that's a really good idea. Question?
You mentioned pointers aren't in the implementation, but were you sort of suggesting that they are kind of worked out in the...
So we've seen examples where it'd be really useful to use them. The Haskell interface file has, like the second piece of the information is a pointer to a data structure that is like a dictionary that's then useful for the rest of the data. So it would be useful to have that kind of thing in the language, to be able to describe this field as a pointer to this particular location, to something that's going to have this type. We've kind of worked it out in the theory. In the implementation, that means you kind of have to scan forward and then scan backward. And we haven't had a user who cared enough about it to make us go ahead and do that.